Hello, everyone. My name is Ahmed Najafi, and I'm Vice President of the RTTA under the name of the largest scale structural system and optimal design. This is our monthly webinar, and actually the last one during the academic year 25-26. And I'm so excited that we have two talk from Dr. Aaditya Chandrasekhar and Dr. Brianna Macnider. So we will have these two talk back to back. So the structure of the today webinar will be, we will first have a talk from Aditya and then Q&A for a few minutes. And after that, we will go to the second talk with Valeria. And please write your question when the presentation started, and I will try to monitor, and during the Q&A, you can even have a chance to unmute yourself and ask directly from the presenter. So first, we will go to the first talk. So I will read a short bio of the Dr. Aaditya Chandrasekhar. So he is a postdoctoral researcher working with Professor Wei Chen from Mechanical Engineering at Northwestern University. His research interests include machine learning for computational design, topology optimization, differentiable simulation, and computational mechanics. Prior to his current role at the Wei Chen Lab, he was a postdoctoral research at Oregon National Laboratory. He received his PhD in mechanical engineering from the University of the Wisconsin-Madison. With this, Aditi, floor is yours. So thank you.
Wonderful. Nice to see the crowd over here. And I'm happy to participate and share some of the things that we have been working on at Northwestern over here. So to give the broad setting, this is to do with topology optimization, in particular design optimization with compositionally graded alloys. We are dealing with applications for high temperature applications, particularly turbine blade design. I'll go into a bit of the design and the problem that you're working on. And two particular solutions that we have been working on is one for modeling for creep deformation. The other is manufacturing constraints when it comes to manufacturing with compositionally graded alloys. So just a quick overview. So just quickly talk over heterogeneous system, what they are, where they're used. Talk about turbine blade design with functionally graded material. And then address some of the challenges when it comes to modeling creep and nonlinearities, and then finally talk about manufacturing with gradation control. So just to sort of set the setting over here, most of this, designs that we see today are made up of, like more of a homogeneous material, but more often than not, one would really benefit if we had access to a heterogeneity in the design. For example, take the turbine blade over here, and near the bore, you could really have, for strength and fatigue resistance, maybe if you wanted like fine grain, this one. Near the rim, maybe you wanted to go for something like a coarse grain for creep resistance, and then at the turbine blades, you really want something, large, really grain single crystals for strength, oxidation, and so on. So that's kind of the motivation that we started on. And the other things that we work on in the lab are things like soft robotics, where once again, if you wanted to sort of program in some functionality, into the response of the material, you want to have a heterogeneous material system, as well as things like optical cloaking and so on, where you can have some kind of optimized material distribution to get things like your cloaking. Optical cloaking. So that sort of sets the stage for us to why one would even think about designing with a heterogeneous material system. And to maybe go into a little bit more detail, maybe I'll talk about the actual project that we're working on. This is a DARPA challenge on the design of turbine blade, part of the metals project. And their design goal is essentially to come up with like these turbine blades and turbine rotors, where essentially they want to go for about 100 degrees increase in temperature, while they want to reduce 50% of critical material. So these are things like, titanium and so on, where you really don't want to use more of these critical materials in your designs, given, a lot of issues going on globally, as well as, for weight reduction and so on. So that's kind of the broader motivation. And this is their design goal. And they want to do this, achieve things like design optimization. And their goal is to also achieve this within like a 12-hour time frame, on a decked out computer with about like a 10 million degrees of freedom, and want to consider oxidation, creep, and other kind of design constraints. And the key idea that they have been pushing on is that one material for your design is too restrictive. So the design requirements are so high that you really can't do it with a single material. And that's the motivation to go for something like a functionally graded design, where you sort of change or the composition locally depending on your need. But it's a harder problem. To build the cat, so to speak. The reason being that you're now dealing with a high dimensional, uncertain material space. And the question comes down to how are you going to represent the design, how are you going to analyze it. You have like non-linear systems with transient non-linear multiphysics. This one, the optimization becomes the objective functions. The constraints are pretty difficult to express and compute sensitivities for. And finally, you also want to ensure that the design is manufacturable. So how do you incorporate some of these manufacturing constraints? So that sort of sets the broader framework as to the problem that you're working on. So what we did is like we started with some kind of a baseline study where we were even questioning, can we do a concurrent design of your material and geometry? And the key idea is that also we are doing a non-linear material properties. So where we are doing a thermoelastic simulation, and the temperature dictates the material properties as well. And and we want to do this in a sort of a closed loop topology optimization framework. And one of the key challenges that we came across was like, okay, the sensitivity expressions are kind of starting to swell up, and how do you do this in a nice and easy manner while being efficient? And that's where we have been working on things like differentiable simulation, where we sort of express the whole computation in JAX. JAX is a machine learning framework, akin to PyTorch and TensorFlow, which essentially helps you express all your computation pipeline, the computational graph, in an end-to-end differentiable framework, so that you can get these sensitivities, without much hassle. And that's been sort of the driving force behind some of the lot of things that we have been doing. And just to show that, and the first thing we want to show was that functionally graded materials do perform better than baseline single material designs. And so we took this kind of a turbine blade design, and we had like a factor of safety constraint, and then we were looking at a trade-off between the material cost and factor of safety over here. And for simple example, we just took like two simple materials, Inconel and stainless steel. And what you see over here is that the more you move towards the bottom right, it's a worse design, and you get to the top left, you have a better design. And what we did find was that compared to single material designs, like say just using SS or Inconel, as well as using simple homogeneous design, you could have a much better design if you sort of optimize the the placement of these materials judiciously in optimization. So that sort of was the initial motivation factor that one could get a better performance if we were to consider functionally graded, compositionally graded alloys in our design. That sort of next step was to motivate us was to, okay, now that we have this baseline, can we do creep? And so the idea behind creep is that, again, these turbine blades, they are cyclical, they undergo large centrifugal loads, and then creep accumulates over a large lifespan of the device. So you want to really ensure that you maximize the operating time of these blades. So the challenge essentially from an optimization perspective is that it's a transient problem with a really large time span that we are looking at. It's highly nonlinear problem, and this sort of these nonlinear transient multiphysics adds to the complexity of the problem. And the first thing we wanted to show was that, hey, can we just do a single material topology optimization where you have this the age-old tip cantilever beam, where you were just looking at a simple knot and creep, just a structural deformation problem. And we were wondering if one can even minimize the creep deformation at the end of its lifespan. So just like a simple illustrative example. And what you see over here is that at the end of its 50-hour lifespan, the creep displacement is much lower in some sense than the tip displacement without creep consideration. So this sort of sets the stage for us that one can, in fact, optimize for creep lifetime, considering with topology optimization. So we sort of extended this and said, okay, now can we do something more interesting where, we don't have a single material, but rather we have, again, once again, for simplicity, just two materials in our mixture. And we were looking at something like a cost constraint, where, again, the objective was to minimize the final displacement after the creep, the structure has creeped. So what you see over here is that on the x-axis is time and y is displacement. And the key idea is that if you were to just go for a simple material like, SS, you would, you could end up with really cheap design, but then you have a really large displacement. But if you could go for, maybe a 50-50 mixture, maybe you get, a much higher cost, but then, your displacement is differently lower. But if you were to really optimize the location, the position, the distribution of these materials, you can go for a much lower cost while, having a much lower creep displacement. So that sort of motivated us that to fact that, yes, you can do creep-based topology optimization. It is important, and doing with graded alloy is sort of the best way to go forward when you want to both manage cost as well as look at the displacement foil. So that sort of sets the idea that, well, we really want to go towards, making components with great design. But now came the question as, okay, how do you in fact manufacture them? And, lo and behold, additive manufacturing is something that has, well positioned to, build this CAD. Idea being that you can do a precise control out of position, vary the composition locally, and so on. So, we were, in fact, we are using like direct engineer position for our manufacturing process. And this is, for example, a part that we fabricated here at Northwestern, where, you go from something like simple gradation along the z-axis over here, being from Incon 625 into Incon 718. And this is, again, results from literature, as well as fabricated parts like, like a rocket nozzle or a graded turbine from literature. So the key idea over here is that it's precedent in literature to go for compositional graded alloy for high temperature applications, particularly when you want to reduce criticality as well as look at performance metrics. But now the challenge comes down to, okay, how exactly, what is the fabrication thought process that goes behind this? And one of the key ideas is that you have some limitation as to how graded your structure can be. So if you were looking for some 100% of A, and you are looking over to switch over to, say, 0% of A, you really need to, you end up having some kind of a gradation. And that's essentially something that has driven us in terms of, the fabrication constraint. The other constraints things are like, for example, material jetting, does allow for in-plane variation. But things like, for example, classically, powder bed fusion, you were stuck with a single material across the layer. As well as you also want to ensure that, you don't get large thermal stresses. You can imagine having two dissimilar materials next to each other with different thermal expansion, and that sort of causes like this a large a differentiable expansion, and so you want to really avoid those as well. So sort of the challenge comes down to the fact that you have a you want to manufacture graded design, and you want to incorporate gradation constraints into your optimization problem. And the way that we have done this is using things like implicit neural representation for the design. And this is something that, in fact, like I worked on during my PhD days, where, the key idea is that you have like different ways to represent design, like density-based method, level sets, geometric primitives. And, we sort of like, it's kind of still debatable, but you can look at different metrics like, okay, how well-defined the boundaries are, how many degrees of freedom, what kind of resolution do you get, what kind of do you get a continuous or discrete representation? So we sort of looked at many of these metrics, and the most important for us was the fact that you get a continuous and a resolution independent representation. And that was sort of the motivating factor for us to go behind within, sort of a neural network-based design representation. I could go into more details about what this is, but in favor of time, I'm kind of quickly glossing over this. And again, there's a lot of literature when it comes down to what exactly these neural networks are. And one of the networks that we found really useful for this work was things like band-limited neural networks. And this has been shown in literature. For example, if you want to control the resolution of the design, you can go for sort of a spectrally parameterized neural network, where essentially by tuning the spectral allowance of this network, you can sort of have a hard cutoff in the frequency spectrum of the things that you can represent. So this is something that we found quite useful. The simple reason being that, if you want to get something like, for example, a smooth versus a sharply graded design, looking at it in the frequency spectrum, this corresponds to having a higher frequency versus a lower frequency design. So the key idea is that, if you want to have gradual variation in composition, corresponds to a low frequency in your design. And just to showcase that we can also kind of prove this mathematically, that you have this an inequality in literature that just shows that the gradation is controlled by the band limit of the representation. So sort of we put these two together, so implicit neural network with a band limited representation, and the fact that we wanted to have spatially graded spatial gradation constraint. So we sort of put those two together to get the fact that one can use this kind of representation to implicitly control the gradation in your design. So we just went with a classic kind of a TO framework, but here instead of using a sort of an element-based representation, we used a band-limited neural network to represent the material distribution at a single point. We did like a thermoelastic design optimization. Then just for just showcase over here, we did like a compliance with the volume constraint, a classic TO problem. And the idea is that by tuning the bandwidth of the representation, one can achieve different gradation. As you can see over here, it goes from like a smoothly graded design to a finely graded, a lot of gradation in your design by just tuning the bandwidth of your network. And once again, we use things like JAX to express this whole computation and end-to-end differentiable framework. It's sort of the whole idea of automatic differentiation sort of picking up steam right now. In fact, I know like Lawrence also has his own MFEM or something for graded design, and so that's something that we really focused on in this work as well. Just to showcase that one can also apply this for turbine blade, we extended this to a large-scale problem where things are simple problems still, but a compliance minimization with the mass constraint, where one could in fact control the gradation of the design to ensure that the design fit the bill for manufacturability, as well as be the optimal performance and meet other mass constraints. So sort of to conclude, just 2 or 3 takeaways kindly over here. The key idea is that construct compositionally graded alloys for your design, be it turbine blades, soft robotics, metamaterials. It has plenty of advantages where essentially you tailor the local material properties according to your needs. The second thing to take away is that differentiable simulation is really picking up steam right now. And the key idea over there is to ensure or to enable you to perform optimization problems that you perhaps couldn't do previously, given the complexity of the problem. So as the complexity of the optimization problem grows, you might want to switch over to things like differentiable simulation. And finally, the idea about implicit neural network representation is a sort of a different way of parameterizing your design. And the key takeaway over there is that there is a lot of literature when it comes to what are the different sort of the advances that's going on in the field of machine learning, from let's say an image representation that one can adopt to things like, for example, graded design and so on. So the idea is that there's a lot of overlap and ideas that are being expressed in, like, say, your machine learning community. That's definitely helpful for us from manufacturability or design optimization perspective. So I think that sort of concludes this main idea that I want to convey. Some of the things that we are working on, and I'm more than happy to, there are people over here who have much better idea, are things like looking at deleterious phases. So the idea is essentially that, you don't want, not all the phase in your phase diagram are, some of these phases might have brittle phases more. So you definitely want to avoid them in your design. So how do you incorporate those constraints into your optimization? That's something that we are looking at. And things like fatigue, oxidation, or something also that's pretty critical when it comes to turbine blades. A lot of open space for that for folks to work on. Again, we try to speed up the computation in many ways we could, but the idea also is that, can we do more advances given that we are now moving more and more towards, highly multiphysics, nonlinear and transient problems. So that's one thing. And of course, it goes without saying that, there is definitely a lot of efforts going on when it comes to experimental validation and verifications over here. So I think that sort of sets a broad idea about, and I hope, I'm hoping for questions at this point.
So thank you very much. Thank you. Any question?
I had a question.
Hi, Ryan, go ahead.
Hi. Yeah, first of all, thanks for the talk. That was really cool. When it comes to the deleterious phases, do you have any ideas for how to traverse that composition space so that you can get, avoid deleterious phases in the graded designs? I know there's work coming out of Rich Malik's group at Texas A&M where they're doing some level set approach, sort of like a nested level set approach, so they can control the different alloys that you step through in a sequence. But yeah, I think it seems like a difficult problem to tackle.
Absolutely. In fact, yeah, this Richard Masco, and then that's also like I think Texas A&M Raymond this group that are working on this particular problem of. In fact, I think this images might be even from his group. I might have credited it somewhere. But the understanding is that the way that we are tackling this problem is looking at things like automatic integration. The idea is that, if you have composition A and composition B, the idea is that you want to avoid, if you have two different elements next to each other, one at composition A, the other composition B, the way we are looking at it is in the traversal between these two compositions, you don't want to hit any deleterious phases. And so we are sort of looking at, doing an integral between these two phases. So that's one idea that we have pushed on. So I don't know if there is the idea that, helps tackle this problem. In fact, as you rightly said, as the composition space grows larger and larger, it becomes a much more harder problem. I think they're doing like graph-based traversal over here, but even that, they show for 3 composition, but in fact, if I recall the paper for higher composition dimension, it becomes a harder problem. So I don't know if there's a silver bullet for this, but nevertheless, I would definitely agree it's an interesting problem to look into.
Awesome. Thank you.
So thank you. Any other question? Okay, I will go. In slide 17, you showed the design of your turbine blade. So here you have a layout, and then you have this gradually actually design your macrostructure. So when you are setting up your topology optimization, for example, for this problem, I think you fix the layout. Yes, the layout is fixed. Just you are working on how to degrade sorry, not the degrade, but gradually change the material macrostructure.
Correct.
Yes.
Correct.
Okay. So have you done anything in the multi-scale that you at the same time you are designing the layout and designing the microstructure at the same time? If not, what is the best approach? Do you have any? You can comment on this.
First question, no, we have not done anything that for instance, optimizes, I guess, the material composition and the and the overall structure. So and to your second question as to what are some of the approaches, the best approach over here. I mean, one can definitely think about like homogenization and so on, where you sort of do like homogenize in the microstructure level and and at the macro scale. But again, the issue that we often run into is like, the explosion and complexity of the problem as well as cost. So I don't know. I mean, to be honest with you, I think if folks who are looking at the, like a machine learning perspective of, like on the fly homogenization or something, could, I think, something that might help in this.
But that will come even with its own limitation, homogenization. If we go periodic, if the material is not periodic, or some of those things about the cost you mentioned. But back to this problem, how you are what is the role of your topology optimization? Are you, for example, when you are discretizing, your optimization will give the composition of material for each element? Are you that is the point that your optimization algorithm will decide that in this part you have what kind of the material or what kind of the alloy you can use? Yes.
Yeah. So in some sense, yes. So just to bring the point back over here, so the idea is that we use like a simple neural network. This maps spatial coordinates to the composition of the point. So the design variables here aren't the the elemental compositions like in traditional density-based optimization, but rather the weights of the network acts as your sort of a pseudo parameterization, which which dictates the overall material layout. So yes, so the question, to answer the question is, we do have at the end of the day like a density-based representation, but nevertheless, the parameterization is something different where we use the weights of the.
Okay, so good. Thank you very much. Any question from the audience? Okay, so if not, I will ask my last question. In here, the neural network that you are using, it is a kind of acceleration, or it provides you a surrogate model that you cannot collect or generate some of the data during your optimization. What is the role of machine learning or AI here?
Absolutely. So there is no data involved. This is I'm sure you're familiar with things like PIN, where essentially they use a neural network based representation to map, let's say, coordinates to, let's say, the field variable and a loss function that mirrors the PDE that you're solving. This is something in the same sort of a motivation where essentially the weights of the network simply maps between coordinates and, let's say, the density variable. So that's the key broader aspect.
So, okay, thank you very much, Adi. Very interesting work and talk. So thank you very much. I appreciate it. So with this, let's transition to the next talk from Dr. Brianna Macnider from Lawrence Livermore National Lab. So, and when she is setting up her sharing her screen, I will go through the bio to save the time for her talk. So Brianna is a postdoctoral researcher at the Lawrence Livermore National Laboratory and a recipient of the Laboratory Residency Graduate Fellowship. She received her PhD in aerospace engineering from University of California, San Diego in 2024. And her current research centers on design optimization for a variety of applications, including structural dynamics, mechanical logic, and smart materials. With this, we will go to her talk. So you can go to the full screen, and
yes.
The floor is yours.
Yes, so thank you for the introduction. I'm Brianna Macnider, postdoc at Lawrence Livermore National Lab in the Generative Design and Optimization Group. I'm going to be talking today about some of our recent ongoing work looking at gradient-based design optimization for structural dynamics. Looking at things sort of from the perspective of structural dynamics can very quickly get you to a point where even for very small, simple structures, you have thousands of time steps that you need to deal with. These represent computational difficulties, and then also looking at how to sort of set up an optimization problem for this type of setup and the difficulties inherent in that. All right. So just starting off with sort of a high-level overview of what optimization looks like here at Livermore. So we have an in-house design optimization code called LIDO, which stands for Livermore Design Optimization. It is built with automatic differentiation in this graph-like structure. The idea here is that we're built on top of this finite element and physics solve code Smith, which handles all of our PDE solves, and then is automatic differentiation enabled, so carries all the derivatives along with it. When you then go to set up an optimization problem in Lido, you design this graph-like structure where each one of these bubbles represents an optimization, an operation that you perform to your data set during your optimization. A couple of key points here. So one is that this is very modular, so it's very easy to sort of go in and take one of these operations, one of these bubbles, swap it out for a different one, or reconstitute your graph for a different optimization problem. And the automatic differentiation just sort of works very well with it, so don't have to stop and redo any derivatives or anything. It happens all for you. Secondly is that this is parallel enabled. So the nice thing about this is we can throw it on the supercomputer and run problems with lots of degrees of freedoms and lots of time steps fairly quickly. And I have just represented here some snapshots from a problem that was run with a very classical cantilever beam density-based topology optimization problem. We're not limited to that. We can do different sorts of optimizations with this setup here. So I mentioned, we're wanting to look at structural dynamics problems. We're interested in things like vibration, random vibration in the time domain with rate-dependent materials and impact mitigation. So we decided to start off with sort of our example problem to explore out implementing this, looking at this very sort of classic egg drop problem. If you think about, like an undergraduate engineering class where you have something like an egg that is fragile that you would like to drop on the ground and have a structure protect it. That's sort of the motivation for this. So you can see our problem setup over here on the left. We have this square at the top that is representing our quote unquote egg that we're calling our protected domain. We are starting off with the density-based topology optimization approach. And this is our starting structure over here on the left, where we're sort of starting off with a array of holes in our initial structure. The entire domain starts off with an initial velocity, which it launches at this bottom boundary that we're calling the ground width. And this bottom boundary has a penalty contact on it. So the idea is that as our structure moves down with its initial velocity, it will cross over this bottom boundary and then get a kickback force similar to having hit the ground. This kickback force is going to propagate up through our structure into our protected domain, and we're trying to optimize to protect that region at the top. On the right over here, you can see this is just what the Ford simulation for this initial starting structure here looks like. We are taking advantage of symmetry to use only half of the domain in our simulation to make things a little bit computationally faster. I think this is still several thousand time steps here, so you can see that this is the velocity wave launching upward from that impact with the ground, propagating throughout the structure. So having described our problem setup and what we're hoping to do and hoping to look at, what sort of challenges are we expecting to hit and have we hit as we sort of move through setting up this problem? So the first is that we are looking at using an explicit time stepping scheme. This is desired for short duration events like impact, but it can require many time steps in order to solve properly, which leads to potentially computationally expensive simulations, even for very small structures. Second, tied into this is that within our explicit time stepping scheme, we do need to size our time step for stability. And it's given that we are doing a topology optimization problem, it needs to be stable not just for our initial design, but for all potential topologies that we could come up with in our optimization. It would be very undesirable to get a couple of hundred optimization iterations in and then have everything crash because all of a sudden a new design that the optimization problem comes up with is no longer stable at the time step that we're working with. So that's important to consider. Third is potential memory issues. So we're not yet to the point where we're running into this, but looking ahead at how things are going to scale up. With automatic differentiation, we do need to store states for our eventual backwards pass that we're going to perform during our sensitivity calculations. So when we have lots and lots of time steps, we have to store a lot of states, and this could become a limiting factor. And then finally, figuring out how to formulate a meaningful optimization problem for this setup. It seems like it should be pretty straightforward, but what we found is that the usual methods for density-based optimization problems to drive designs to something that's both connected and has a fairly binary material, no material representation. These usual methods don't usually work as well in the context of the type of problem we're solving here. So starting off with the first sort of challenge that I mentioned, looking at explicit dynamics, we are implementing a very classic, well-known explicit numeric beta scheme. Equations are shown over here on the left, essentially just sort of moves through and increments based on your time step from one iteration to the next, your displacement, velocity, and acceleration. A couple of points of note here. So there's no implicit solve, which does make things a little bit faster, but the choice of the time step does determine stability. And as I mentioned, it potentially your time step needs to be small, which could lead to having to run this many, many times. And secondly, if you'll notice this last equation down at the bottom here, there is an inversion of the mass matrix that is required in order to calculate the acceleration for the next time step, which, given that we're running a topology optimization problem, we expect our mass distribution to be changing from design to design. So this has to be redone every time and possibly could end up being computationally expensive. So what do we do about these things? So for the stable time step, the point we start off with is looking at what we expect the wave speed in our problem to be. So if we look at the ratio between the stiffness and the density in our elements, we know that our something that will be a good enough stable time step should be as long as our dt is less than the amount of time it takes for a wave to travel across one element. And if we consider the ratio of stiffness to density, that should give us the worst one of these conditions in our problem. This, in theory, should be enough. There are extra complications that get added in later, which I'll go over in a few slides here. But that's sort of a good starting point for this. And then for our mass matrix, what we end up doing, there's a couple of different ways to deal with this. We decided to just go ahead and lump it. So essentially what we're doing is taking our mass matrix, and for every row, we're summing the masses to the point on the diagonal. So instead of needing to invert a full matrix, this becomes a very simple component-wise division problem where we just have a single vector of the diagonal to take the inverse of. So I mentioned that there's a sort of an asterisk on that stable time step that I had mentioned in the previous slide. This asterisk comes from the contact condition that I had described that we were prescribing along the bottom of our domain here. So this over here on the left is some intermediate optimized design, not converged. Doesn't matter a ton, except for the fact that if you look at that bottom boundary there, you can see that part of this bottom boundary has fully dense material as we started off with, and part of this bottom boundary has very low density and part has intermediate density material. And so what we ended up figuring out was happening as we sort of move through these optimization problems is when you have a penalty contact along the bottom there, your stiffness is tied to your penalty parameter, but your density, if it goes very, very low, can skew what your stable time step should be just for those elements along the bottom boundary there. And so you can see over here on the right, we went through this design and sort of interrogated what the energy distribution was like for different regions in the design across a single Ford simulation step. So you can see we have our strain plus kinetic and then strain and kinetic broken out. And you can probably see the problem here is this area 4, this area down here on the bottom right that has this very low density region. Looks awful. The energy is jagged and jumping all over the place. And it also increases from what it started out with initially. You can see this spike at the time step 1 here, which it shouldn't be doing is non-physical. That's not great. And so we figured out, the culprit is that our stable time step, which was stable for a design that had a fully dense bottom boundary to start with, is no longer stable if that bottom boundary is no longer fully dense. So, what do you do about this? There's a couple of different things. One thing we could do is resize our stable time step, but a couple of back of the envelope calculations showed us it would have had to have been a couple of orders of magnitude smaller, which means that instead of running a couple of thousand time steps, we're now running tens or hundreds of thousands of time steps, which we can do, but we'd like to avoid doing just for that bottom boundary condition if we can help it. So what we ended up doing instead was scaling our contact boundary condition along the bottom by the design density. So essentially, instead of just having a penalty times the displacement over the boundary, we now have a penalty times the displacement over the boundary scaled by that design row, which varies between 0 and 1. So the softer elements get a much lower amount of kickback force, and the stable time step doesn't need to be adjusted to deal with that problem, basically. You can see over here on the right, these are the energy metrics again. They look much nicer. Area 4, which is that bottom right area, again, no longer has these jagged issues, and the total energy either remains constant or goes down as time goes on, which is what we're expecting it to do. So this is good. So that was some of the issues with computational issues that we addressed in setting up these types of problems. And now we're going to talk about what it takes to actually formulate an optimization problem in this context. Anyone who's done any appreciable amount of density-based topology optimization has probably gotten results like the ones that I'm showing here, which are bad results. So just kind of wanted to highlight that it seems like it should be a pretty straightforward approach. You know, we have this box at the top, we want to protect it. We can define a mathematical objective that does something to that effect, and you know, it should be easy. But as it turns out, it's really not, because for something like wanting to protect this block at the top, it's the optimizer very often wants to make things softer rather than making them stiffer, which means that the usual method of penalizing your intermediate density elements by having them in sort of a resource constraint with a resource competition with your constraint doesn't work super well. These approaches here do have a volume fraction constraint on them, but the problem is that the optimizer is very, very happy to go down to the amount of volume fraction that you specify, and then just go further down than that and find a good design, good from its perspective, at a lower volume fraction than the one that you specified. It's a non-unique design space, and also if it throws a bunch of soft material in there, then it's sort of similar to it basically putting foam or some sort of like crash or landing pad in the design. And so from a perspective of the actual objective function, this works very well. From a perspective of getting us something that is a connected design that is potentially manufacturable with mostly binary material, this is awful. You know, it doesn't want to give you a connected design. It doesn't want to give you a binary design. So we've gone through with our very modular graph and sort of swapped out what the objective function looks like, you know, move these bubbles around to try and reformulate the problem. Just highlighting some of our quote unquote failed objectives here, which doesn't mean that there's no way to get these to work, but just that we found these didn't work very well for our setup here. So going through trying to minimize kinetic energy, or reducing the max of the acceleration, looking at the area under the acceleration curve, both as a constraint and an objective, and then even going through and trying to add some sort of a connectivity constraint on top, like compliance or some sort of a thermal transport constraint. It ended up that those just kind of dominated the problem largely, and it didn't work out very well. So we did come up with a workable approach. So what we finally landed on was a flat acceleration profile is our target objective, but not just flat, but flat at a specific value. So rather than just saying try to make the acceleration profile flat, we say make the acceleration profile flat at you know, X value meters per second squared of acceleration. This requires the optimization problem to have something that is mostly connected, because the only way for the block at the top to have an acceleration is for the stress from the contact at the bottom to be able to actually propagate up into it. And so in order to achieve some value of acceleration, it has to be connected. Then on top of that, we add a gray constraint, just a constraint on top that says you can't have more than X% of the material be gray, and then run this optimization problem, and then follow it up with a follow-up problem that has the target acceleration objectives that we've achieved, imposes a constraint to sort of keep the behavior where we want it, and then minimize the mass to try and get a nicely converged design that looks clean. So these are some slightly better results. This works pretty well so far from what we've seen. So you can see over here on the left, these are just a couple of the problems that we've run with slightly different acceleration targets. So the two on the left, the one on the far left has half the acceleration target of the one in the center here. You can see that the optimization problem changes sort of the distribution of what these angles and lengths on these struts look like in order to accommodate getting the amount of acceleration that we want in our protected domain. And then the acceleration does end up pretty flat. So we're expecting that we're not getting a lot of stress spikes in our protected domain up here, and it is decelerating without slamming into the ground. So this works pretty well. The design on the right over here is our first attempt at adding in a rate-dependent material. This is sort of ongoing, but we can do it, and we get slightly different looking designs from this. And then on the far right over here, you can see this is what our acceleration profile over time looks like for both our initial iteration and then also one of the optimized iterations. So you can see it does a pretty good job. Our target here was 30, so it manages to hit that target pretty closely and then have the acceleration profile be fairly flat throughout the time that we're simulating. So that's all well and good, that's great, but we had a suspicion from looking at some of our energy plots that there may be some effect from what is supposed to be void material here. So, we're doing this density-based optimization, which means our material in this blue region isn't 100% void, although it's close, but also we do have this sort of soft intermediate material between our fully dense domain and our void domain. And from the energy plots, it looked a little bit like there was some energy either being stored or propagating through these regions. So we took the extra step of going ahead and thresholding our design and making a conformal mesh out of it, which does change the design a little bit, but we got it pretty close. It looks like it's mostly the same shape. And then running the simulation again. And so you can see over here on the far right, these are the acceleration profiles of these different runs. So the topology optimized one is this blue dashed line, looks very good from an objective perspective. It's pretty much exactly the behavior that we wanted it to have. And then we take this same design and make a conformal mesh out of it. And the first iteration doesn't look nearly as good. It's got this orange dashed line here. It's got all these spikes. It's still sort of hovering around the target value that we had, but it's not nearly as flat as it was. So there's some difference here in the behavior that we see between our density-based representation and a conformal representation. Now, part of this might be because we did threshold the design, but after doing some energy interrogations, it looks like there's a great deal, not a great deal, but at least a significant amount of energy in the topology-based representation design that is being stored as strain energy in some of these low-density regions of material. So there's not a lot of kinetic energy, there's not a lot of wave propagation going on in the low density materials because the mass is so low, but there is enough energy being stored as strain energy in low density materials that you can see it show up. So we took our conformal representation of our design, and I mentioned that the Lido graph isn't restricted to topology, density-based topology optimization. So we ran it through a shape optimization algorithm, made a couple of small changes here, and then you can see we pretty much got close to recovering the type of flat acceleration behavior that we were targeting here. And this is just showing what that full design looks like with the full domain simulated with our explicit dynamics. So this is the velocity profile that's moving as the color ramp here that you can see. So you can see by the end, our protected region at the top goes down to the blue field, which is a velocity profile of 0. So we decelerate it down to 0. And finally, to finish up here, I had mentioned that one of the potential limiting factors that we might be running into soon is memory. So we haven't run into this yet, but as we've now have all these things implemented and working, we're expecting as we add more, move to finer meshes and move to 3D, that we're going to start running into more issues with the computations taking longer, and then in addition, the memory that is required to store the intermediate states might get a little bit unwieldy. And so one of the solutions which we have in place ready to use, although we haven't had to use it yet, is a checkpointing algorithm. So the idea here being that you store only a finite number of your intermediate states optimally distributed, so that when you do go to do your backwards pass-free sensitivity calculation, you can't store all of your states, but you can look at whatever the last checkpoint that you saved was and basically redo the calculations in between that point and where you are in order to do your backwards pass for that. So this does add computation time, but it does get around the memory issue there. And with that, I'll say thank you, acknowledge all of my wonderful coworkers and teammates that have contributed to this work, and happy to take any questions.
Thank you very much, Brianna. Appreciate. So any question from the audience? Okay, to start and give time to people to type their question. So how you come up with this flat acceleration? You said that you selected different value. It was try and error to find which flat acceleration will give you the solid connected geometry, or it was based on a physics or physical understanding?
Yeah. So it is I will say this isn't this is a problem that we sort of made up. So it is a little bit arbitrary right now. I will say that right now it is a little bit of trial and error. So I sort of look at what the acceleration profile looks like from the first iteration, and just choose a value that I is lower than that. That looks good. That said, there's no reason why you couldn't do it from a physics perspective. We just haven't really bothered to do that yet. But it is true that if you choose an acceleration profile that is very low, that the optimizer will still want to make a design that has very soft material in it to try and achieve that. And so there is a connection there between this amount of starting velocity that you have and then the time window that you're simulating over, and how quickly you want to decelerate. You will reach a threshold in which you the optimizer won't want to have a fully dense design again. And at that point, I think you could probably bump up the grade constraint a little bit, but there will be a limiting factor there.
Okay, so and how this flat acceleration force the algorithm to give this fully connected the material that support that protected area physically? Do you have any interpretation for that? Why the help the optimization come with this design?
Yes, yeah. So part of the reason this works so well is, so if you'll look at the acceleration profile over here on the right, so our block starts off with a starting velocity, but there is nothing, no forces acting on it if it's not connected. So it'll start off with the starting velocity, but unless it has a stress wave or a kick that it gets from somewhere, there is nothing that will give it an acceleration. And so the only way for the block to have a non-zero value of acceleration, the only way for it to actually slow down is if it does get force coming in from somewhere. So in this case, the only force that we're imparting into the problem is coming from this kick at the bottom. And so the only way for the block at the top to get a non-zero value of acceleration is to have a stress wave travel up from the bottom and reach it. And because this material here is very soft in the middle, it doesn't do a very good job of transmitting that force. So the best way for it to get some non-zero value of acceleration is to have a connection to the bottom of the design domain.
Okay, so thank you. Any question from the audience?
Yeah, I had a question.
So go ahead, Brandon.
Yeah, first, thank you for the great talk. I was curious to know what you think the impact of scaling the contact force with the density is. Like, how do you think that affects your results versus just like lowering the explicit time step size and running this thing for 10,000 or 100,000 iterations?
Yeah, no, that is a good point. It is something that we've considered when we were first coming up with the idea of scaling the contact force. We were worried that it was going to run into designs where it basically lead it to not want to have anything connected still, because it was potentially going to mess up with it wanting to do connections to the bottom here. I will say it seems like it's worked well so far for still figuring the optimization, still figuring out that it needs to have something connected down at the bottom. I guess the difference I've seen so far is before we scaled the contact force, a lot of the designs that we were getting had a wider base at the bottom. So this one over here on the right actually was one that was run before we had scaled the contact force. And so you can see it's got a great deal more contact at the bottom than the ones over here on the left do. So it's I think probable that it is changing the types of connections that you get and the types of designs that you get, but also it is true that this is a very non-unique design space. And so I think most changes that you would make to the problem would have that same effect.
Okay,
cool. Thank you.
Okay, so before so we go to the Solberg question. So here I see that you are doing this for linear and nonlinear material. What is then your nonlinearity? It is the material nonlinearity or geometrical nonlinearity?
Yes, so all of these have geometrical nonlinearity included, but on the left over here, this is a Neo-Hookean material model. That's the nonlinear here. And one of the things I didn't quite have time to touch on, just because there were a lot of factors that went into this, is that we are doing an interpolation. So the soft material here is linear material, and then the fully dense is a nonlinear Neo-Hookean, and we're interpolating between the two. And this is an additional step to help with the stable time step. So one of the things that we were running into was that in some of our simulations, the very, very soft elements can deform a lot. And so if they are also nonlinear, then you can end up in a situation in which the local stiffness sort of spikes because of the material model. And so it's helps a little bit to have the soft material be linear to avoid those stability issues.
Okay, so and I'm reading the comment by the Solberg. So the comment is that the penalty scaling is pretty common. That's you would do in a standard explicit code based up on the modulus, etc. So that is the comment by Solberg. So with this, because we are hitting the 3 p.m., so thank you very much, Brianna and Adi. So really appreciated your great talk and presentation, and thank you for everyone joining us in this last webinar for our TTA, large scale structural system and optimal design. Be tuned that we will send out the new series of the talks for the new academic year, and we are trying to have even a conference for next year. So be tuned. We will send the announcement for all of this. Thank you very much. Appreciate.